All right, so now let's think about how we can use the divide and conquer paradigm to build better algorithms. And in the process, we'll be able to think about how we can analyze those algorithms as we design them. So let's think about sorting. So we've talked a very little bit about sorting so far. I told you to go look up some algorithms, and most likely you've run into some elementary sorting algorithms in your earlier programming classes. In fact, you've probably run into this sorting algorithm as well at some point. So sorting algorithms, you know, if you take a brute force approach, a sorting algorithm can be quite slow. So what the notion of something like selection sort or insertion sort does is it says something like this. Let me walk down the array, element by element, and then do something with all the rest of the array at that element. You know, something along those lines, right? So this is the notion that we might see. We might say, hey, let's start here, and then for this index, I'll go traverse whatever remains of the array and go find the element that belongs here. Go find the smallest element and return it to this spot. So what that means is, you know, I have to go here, 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 here. And then I'm done with my first kind of iteration of my outer for loop. And then in my second iteration, what I'll do is I'll go here and I'll say, all right, now I'm going to go traverse the rest of the array and go find the thing that belongs here. And then I'll move here, go traverse the rest of the array. So elementary sorting algorithms that do something like this, whether they be insertion sort or bubble sort or something along those lines. Just a moment, I've got a streaming problem. All right, so whether they be insertion sort or bubble sort or selection sort, tend to have two nested for loops that give us this triangle of operations, right? So elementary tends to be n squared. And I'll say big theta of n squared. So let's think in a divide and conquer mentality and see if we can do something better. And so what we're going to try to do is build a sorting algorithm that does something along these lines, right? And it helps to think in a recursive way. So let's think about what divide and conquer sorting might look like. Well, it might look like, you know, we taking an array and then dividing it into chunks, right? That's the divide and conquer step one. Recursively sorting each chunk and then recombining them, right? So it might say, hey, recursion, go solve those two chunks. And then once you've solved them, bring the answers back to me, and I will combine the answers that you gave me. And so, you know, let's think about how we might do something like this. And so this kind of mentality of breaking the input into chunks, recursively solving each chunk, and then recombining them, is the guiding philosophy behind an algorithm called merge sort. So let's think about how merge sort works. So as the name implies, the key operation in merge sort is merging. And so this is sorting by merging sorted arrays. And so here's the notion. And I'm just going to work through one full run of merge sort, just for your benefit. So suppose I have an 8-element array, 5, 4, 1, 7, 3, 2, 9, 8, 9, 8. So what merge sort will do is it'll cut this array in half, or as near to in half as it can get. So it'll cut it into these two pieces, and then it will recurse. Okay. Once it recurses, right? So it'll take these two halves and send them to new instances of the merge sort algorithm. So then when it gets those, and say, go sort these, right? So it'll say, hey, sort that first one, sort that second one, and give me the answers back, right? Give me sorted arrays back. Once it gets sorted arrays back, it will combine those two arrays, those two sorted arrays, into another sorted array, right? And then it will return that result back up. So, you know, it can be helpful to actually run through this completely to see what's going on. But that's the notion, right? We're gonna take these arrays, tell merge sort to sort them, however that works, and then when we get it back, when we get these two sorted arrays back, now in a sorted fashion, we'll just combine them back together, right? And so then we'll hopefully be able to get some algorithmic benefits by doing this. So what does this mean? Well, so let's send them down. So we'll recurse on these two arrays. So when you recurse on the arrays, what does that mean? Well, now we've got these two arrays that are being handled by two copies of the recursion. So I'll draw that like that. And so then what these two arrays will, the thing that the merge sort algorithm will do with these two arrays is it'll split them in half and send them to merge sort again, right? So it'll just send them down the chain and say, hey, I don't know, these aren't sorted, go sort these. And then when it gets them back, it'll merge them and send them back up, okay? Merge them into a sorted array and send them back up. Okay, so now, what happens next? Well, we've got 5, 4, 1, 7, 3, 2, 9, 8. And so the next step down, right now, this one has been split into 2. This one's been split into 2. On the next step down, we've got these now four as yet unsorted arrays. So what the merge sort algorithm will do is, again, it'll split each of them in half, send them down, and say, hey, sort these and give me the results back, and then I'll merge them into sorted arrays and send them back up. Okay, so what that looks like is now it splits these in half and sends them down again, right? So it sends down 5, 4, 1, 7, 3, 2, 9, 8. So now what do we have? Well, we've got 8 one-element arrays. Okay, so I just do this to be totally complete and say, hey, we've just recursed on these we've just sent these one-element arrays down to the merge sort algorithm. So what the base case here is going to be if the array has one element, then it is sorted. So we'll just send it back up. We'll just return it back up. So once it returns them back up, right, what happens? Well, this is where the merging comes in. So if I take 5 and 4 and return them, and they get returned back up to an instance of merge sort, what that instance of merge sort will do is it will say, hey, these are two sorted arrays. Now I'm going to combine them together into a sorted array. Right? So how do I combine 5 and 4 into a sorted array? Well, I just swap them. I just write 4 and then 5. Right? So now I have the beginnings of things that look to our human eyes like sorted arrays. Okay, so this is 4 and 5. Now 1 and 7 get passed back up. And they're already in order, so we keep them as 1 and 7. 3 and 2 get passed back up, and they are not in order, so they'll get put in order by the merging algorithm. And then 9 and 8 are out of order, so they'll get swapped as well. Okay, so now see what we have. Now we have 4 two-element arrays that are each sorted, right? Because they are merged variants, or they're merged versions of 8 one-element arrays, right? And so all that's happened, the only work that's happened so far is that we've split a whole bunch of times, and now we've done a little bit of swapping, right? We've done a little bit of effort to make sure that these arrays that come to us sorted now get put together in a sorted way, get merged together into sorted arrays, right? So what happens when we merge these two? Well, those are two sorted arrays. Right? So each of those two-element arrays is sorted. So if we merge them together, we should merge them into a sorted array. So we'll take the 1 will be first, and then the 4, and then the 5, and then the 7. Okay, so we've just merged sorted arrays into a sorted array. These are already sorted as it happens, so 2, 3, 8, 9. Okay, and then the very last step is to take these two 4-element arrays that are now sorted and merge them into a sorted array. Okay, so we get 1, 2, 3, 4, 5, 7, 8, 9. There it is. Okay, so then those are merged together into sorted arrays. Right, so there's no, if you want to think about it like this, there's no real sorting that gets done in merge sort. Right? All we do is split until we get to one-element arrays, which are sorted by default. And then we take a bunch of sorted arrays and we merge them together into sorted arrays. All right, so now how do we think about this from the standpoint of divide and conquer? Right? So how does divide and conquer work? Div and conc. Well, divide and conquer says first, what do? We split the problem into chunks. So we split. And then so as we write this list, let's associate a complexity, or a time function for merge sort for each of these cases. So what does our splitting look like? Well, in merge sort, we're taking an array and cutting it exactly in half. And so let's say it takes s of n time to split an array. Right? So this is time to split array of size n. Okay. Number 2, what do? We recursively process each chunk. So recursively process. Okay, and so I can say, you know, this is sort of our 2 times t of n over 2. And so what do we have here? Well, we're going to recurse twice. So we have a 2 times t of n over 2 because we're recursing on arrays that are half the size of the original. And then in the end, we're going to combine. Right, so once the recursion is done and it passes us back answers, we're going to combine those answers together into something that's useful. So our combine, I'll call this c of n. And this is the time to combine sorted arrays into sorted arrays. Okay, so this is time to combine sorted arrays into a sorted array of size n. Of size n. Okay, so now what's our t of n? Well, the divide and conquer recurrence relation says our t of n is equal to 2t of n over 2. Right? Why 2t of n over 2? Because we're recursing twice. Right? There's always 2 halves, and each of those halves is half the size of the original. Okay, so we can find our a by how many times we recurse. We can find our b by how much our problem is reduced in size. So 2t of n over 2 plus s of n plus c of n. Okay, and so this is the recurrence relation for merge sort, right? Where that's our splitting overhead, split overhead. And that's our combine overhead. Okay, so how do we think about this? Well, fundamentally, we need to plug in functions to s and n. Right? We need to actually say, all right, s is this, c is this, and then we can go proceed and analyze. But before we do that, we'll do that in the next set of videos. But before we do that today, I want to think about what results we could get. Right? What might s and c, or what different values for s and c might give us interesting results. And first, what we could do is we could actually notice that the split overhead is constant time, right? So the question is, do these splitting and combining functions or methods or whatever you want to call them, or algorithms, do they depend on the size of the input? And the splitting does not. Right? All the splitting has to do is take n, divide it by 2, floor it, and then plug that in as an index. Right? So there's no dependence on n for the s term. So s of n is constant time. Okay? Because it doesn't depend on how big the array is. Right? Cutting an array in half doesn't matter whether it's 1,000,000 elements or 1,000,000,000 elements. All you have to do is find the middle point, and then it's cut, right? Then you're done. Okay. So we could ask, how does the complexity of this algorithm depend on different hypothetical values for c of n? So our question could be, how does t of n depend on c of n? Right? Since s of n won't come into play because it's constant time, but c of n could. Right? So, for example, what if for some reason c of n was quadratic? So what if C of n was big theta of n squared? Well, then what would we have? Well, we would have A. I mean, we can just plug into the master theorem and say, in this hypothetical world where it takes quadratic effort to combine two sorted arrays together, well, what complexity would we get? Well, we'd have A is 2, right? A is 2 in the master theorem recurrence relation. We'd have B is 2, and then we'd have D is 2. Right? So D would be 2. So what's B to the D? Well, that's 2 squared, which is 4, which is greater than 2, which is A. So we'd be in the case where B to the D is greater than A, which is the case where the overhead is dominating, right? And that would give us that T of n would be big theta of n squared, okay? So this is the complexity that merge sort would have if the effort to combine two sorted arrays together were quadratic, right? And so this is it's just a hypothetical. If the combined function is quadratic, then merge sort is quadratic. What if the combined function is linear, right? So we're just playing with hypotheticals at this point. So what happens if C of n is actually linear? So there's one possibility. Here's another possibility, right? What if C of n is big theta of n? Well, then what do we have? We've got A equals 2, B equals 2. Those haven't changed. But now our D equals 1. D equals 1. It's because n to the 1 is equal to n. And so B to the D is 2 to the 1, which is just 2, which equals A, right? We've got equals all the way across, so we're in the balanced case. And what does that tell us? That would tell us that if indeed we can do our combining in linear time, then merge sort's complexity is n log n. Okay, so now we have something to shoot for, right? Now we can say, let's try to get an n log n complexity and see if we can pull that off, or by particularly choosing our combined function to have a linear complexity. So now that's for the next set of lectures, that'll be our goal. Our goal will be, can we combine two sorted arrays together in linear time? And if we can, then we're able to inherit this n log n complexity for merge sort, which is a significant improvement upon the n squared complexity of all the elementary sorting algorithms. So our goal is combine or merge two sorted arrays in big theta of n time, in linear time. And if we can do that, then we'll have an n log n sorting algorithm.